thanks to Hung for the invitation. It's a shame that we can't be in the same room together for this, but one of the bright sides of the pandemic is that we get to meet up with old friends and colleagues around the world in such a convenient way. So thanks a lot to Hung for organizing this sort of thing. It's really great. So let me mention that from the top here, everything that I'm going to talk about is joint work with my colleague from Carnegie Mellon, Giovanni Leoni. So my plan here is to tell you about traveling wave solutions to the incompressible free boundary Navier-Stokes equations, but to properly describe those, I first have to tell you what the standard dynamic free boundary equations are. So I'm going to start off with a review of that. So for the experts in the room, this will be a little bit boring for a few minutes, but we will soon transition into new material. So the idea here is that we're going to consider a layer of incompressible viscous fluid in dimensions where the physical dimensions are 2 and 3, but actually the results that I'm going to prove will be valid in any dimension bigger than or equal to 2. And we'll have a moving domain omega of t that's actually part of the problem. It's an unknown in the problem. And the way that we will think about this domain is in the simplest possible setting where the free surface is given as the graph of a function over the horizontal cross-section. And the horizontal cross-section is basically the bottom of the fluid. And we'll think of this as being completely flat as just a copy of Rn minus 1. We will think that the fluid, when it is at complete equilibrium, is just a completely flat slab of fluid of depth b, and we'll set up our coordinate system so that the bottom of the fluid is at a vertical variable equal to 0, and the equilibrium height then is drawn here in this picture at xn is equal to 0. And then we're going to think of the free surface as being a graph that is a perturbation around this equilibrium height. So in particular, we will think of the free surface as being the points where xn is equal to b plus zeta of x prime comma t, where x prime is the first n minus 1 components of the vector x in Rn. So some notation that I'll use is I will write sigma 0 for the bottom, sigma b plus zeta for the top part here. That's the unknown free surface at the top. And then the fluid domain omega of t is just a collection of points in blue here, where the vertical variable is bounded below by 0, so that it's bounded below by this flat bottom, and above by the free surface. Okay, so you can think about this as a very simple model of the ocean, where the bottom is completely flat and the surface is given as the graph of a function. This is a bit limiting in the sense that the graph formulation does not allow for like wave breaking, where a wave turns over and is hanging over itself. But for very small perturbations of equilibrium, this is a perfectly valid way of thinking about a layer of fluid. So let me now give you the model and tell you the various forces that are going to act on the fluid. We're going to assume that the fluid is incompressible and viscous. This is going to be an essential feature. This is the Navier-Stokes problem, not the Euler problem. And so for every t bigger than or equal to 0, we have to specify, as I told you before, the free surface function, zeta, which is again a function on the cross section. And once we know zeta, this will determine the unknown domain omega of t. And then we need to specify some extra dynamic variables. So we need to specify the fluid pressure, actually, let's start with the velocity field, which I'll write as W here. And this is a vector field taking values in Rn. And we also need to specify this scalar pressure, which takes values in the reals. And I'll write as capital P for the purposes of the beginning of the talk. So this is how we will actually describe the fluid with these 3 variables. We also need to specify the various forces and stresses that are acting on the fluid. So we will assume that there is a constant gravitational field that points down toward the bottom of the fluid. And the way that we will manifest this as a force is in the usual way that you do it in physics. So it'll be the force will be proportional to the density times some gravitational constant, and then just will be pointing straight down with the unit vector minus En. We will also assume that above the fluid in this region up here, there is a constant external pressure, P external. This is just a scalar, and actually is not going to play much of a role in the analysis. It's actually just going to disappear here in a couple minutes. But the main feature in terms of forcing, other than gravity, is this external surface stress. So we will think about this as a mapping from the free boundary, which is changing in time, into the set of in-by-in symmetric tensors. And this, I'll tell you a little bit more about it in a minute, but this will be the main thing that acts as a driving force on our fluid. The other thing that we will account for is the effects of surface tension on the free interface, and we will model this in the usual way with a parameter sigma, which is non-negative. This is just a scalar called the coefficient of surface tension, multiplied by the usual mean curvature operator. And when my surface is the graph of a function, the mean curvature operator can be computed in a very simple way by just looking at the first variation of the area functional, which gives us a sort of nonlinear version of the Laplace operator. So if for instance, this thing in the denominator weren't here, this would just be a standard Laplacian, but this is what you get when you compute the first variation of the area for the graph of the surface. Now, there are several parameters that are floating around. There's the fluid viscosity, there's the density, and there's the gravitational constant. If we rescale in space and time and rename some of the variables, for simplicity, we can assume that all of these things are exactly equal to 1, and we will do this. So then this gives us this system of equations that I've written here. So in the moving domain omega of t, we have the standard vanilla Navier-Stokes equations. This first equation here is the sort of balance of momentum equation in the Navier-Stokes system, which is an analog of Newton's second law that tells us that the forces acting on the fluid, which are these things here, are balanced by the acceleration of the fluid times the mass, but the mass is assumed to be 1 here. The second equation is the incompressibility condition, which is going to enforce the conservation of mass. So probably most of you have seen this system of equations before. What may be new is the equations that we posit on the boundary. These are equations that come from standard continuum mechanics and have analogs with classical Newtonian theory. The first is the so-called dynamical boundary condition that tells us essentially a version of Newton's third law that says that the various forces acting on the boundary are going to be in balance with one another. The first one that we see is actually coming from the fluid itself and is manifest in what we call the stress tensor S. So the stress tensor is the scalar pressure times the in-by-in identity matrix or identity tensor, and then minus the symmetrized gradient of W. So actually, if we had not scaled away the viscosity coefficient would be right here. This object hitting the outward pointing unit normal is a sort of measure of the force generated by the fluid. And it is then balanced by the other forces and stresses that are acting on the interface, one of which is the mean curvature operator, which is accounting for surface tension, as I talked about before. And then the final one is due to external forces and stresses acting on the fluid. So the first term that we put in is the external pressure, which I mentioned before is just a constant, and we will also build in the external stress, which again is going to be the main term of importance in terms of generating non-trivial solutions. Again, I will say more about this in a few moments. The next equation we have to specify is the so-called kinematic equation that tells us how the free surface function gets updated in time as the fluid changes. And it basically just tells us that the time derivative of the free surface function is proportional to the normal component of the velocity with a proportionality constant that's coming from the geometric distortion of the free surface. And finally, we will impose the so-called no-slip condition on the bottom of the surface. So this means that the entirety of the fluid velocity is going to vanish on the bottom. Let me point out one thing, because I will be talking about the stress tensor many times going forward. We have this nice observation that if we take the divergence of the stress tensor, then we get the gradient of the scalar pressure minus the Laplacian of our vector field W minus the gradient of the divergence of W. And so if you come back up and look at these terms that appear in the Navier-Stokes equations, we can rewrite them as the divergence of S. So we can conveniently reformulate the equations in terms of the stress tensor, not only on the boundary, but also on in the bulk. Okay, so that's the full dynamical Navier-Stokes system. This is a talk about traveling waves, so let's talk about those. We're going to assume that the external stress, T external, is stationary, meaning time independent, when it is viewed in a coordinate system that's moving parallel to the lower boundary of the fluid. And we're going to be able to assume that it's moving with velocity gamma times E1, where gamma is just some scalar parameter, the speed of the motion. Now, we can assume without loss of generality that the motion is in the E1 direction by rotating our coordinate system if necessary. So this is not a loss of generality. We can always just choose the coordinates of the E1 direction is the motion that this thing is moving. And why do we assume something like this? Well, you can think about this as a very simple model of a source of stress that's translating uniformly over the surface of the fluid. So probably my favorite way of thinking about this is as a tube of air blowing on the fluid that's held above the fluid and moved along. You could think about this as a very simple model of wind. You could think about it as modeling a ship sitting on the surface of the fluid and moving along at a constant speed, or there are many other variants that you could use in thinking about this as a basic model. So the way that we're going to implement this mathematically is we're going to assume that the time-dependent external stress is given as a stationary function t, which I will assume for simplicity in this talk is only a function on the cross-section Rn minus 1. In the actual paper, we can handle something more general. But for simplicity, we're going to assume here that this thing is just a function of the cross-section variable minus gamma TE1. So it's just a function on the cross-section and just translating along at speed gamma in the direction E1. Once we make this ansatz for the external stress, we then have to make a similar ansatz for all of the other variables. So the traveling wave ansatz for the free surface function, we will call eta. For the velocity field, we will call v. And for the pressure, it's convenient for various reasons to not just change variables by switching to a new variable little q, but to also subtract off the so-called hydrostatic pressure in order to make some other calculations more convenient down the line. So we will make that convention. So the point is that our new unknowns are eta, v, and q in the traveling wave system. The domain itself is still unknown. We don't know the function eta, so we also then don't know the set omega b plus eta, which is the set in which the PDE for v and q will have to be satisfied. So here's a little cartoon. You can imagine, again, a tube being held over the fluid and translated along while it blows air on the fluid. And the idea is that if you're moving along in a frame that is stationary, or in which that tube is stationary, you're hoping to see a configuration of the fluid that is also stationary in that moving frame. Okay. So when you make when you plug in this ansatz, what we arrive at is the traveling wave Navier-Stokes equations, which basically is exactly the same as what we had before, except everywhere where I had a time derivative, I will replace it with a derivative in the E1 direction multiplied by minus gamma. So that's where this term and this term come from. But otherwise, this is exactly the same system as before, except one other thing. When I subtract off the hydrostatic pressure, notice that the bulk gravity forcing term goes away. And what happens is it gets shifted into the boundary. So what has happened to that bulk gravity term is it now is appearing as a term on the boundary involving just the free surface function. So if I had not scaled away gravity, there would be the gravitational constant sitting in front of this term, indicating where it's coming from. The other thing I've done here just for convenience is I've scaled away the unit normal and switched to the non-unit normal, which you can write in terms of the free surface function in this very simple way. This just makes it easier to see what the appropriate linearization of this term of this system of equations will be, because this is a perturbation of just the unit vector En. So one thing that I want to draw your attention to, which is an essential but trivial observation, is that for any traveling wave speed gamma, if we take t, the external stress, to be equal to 0, then we get a solution to the above system of equations just by plugging in v is equal to 0, q is equal to 0, and eta is equal to 0. Notice that setting q equal to 0 here is why, in some sense, it's convenient to subtract off the hydrostatic pressure, because it means then that our sort of trivial solution is 0 for the pressure rather than the hydrostatic pressure. In fact, this is not a surprise because if you assume that our solution lives in standard Sobolev spaces and you posit that there is no source of external stress, so if T is equal to 0, then you can do a sort of energy estimate on this system of equations, and you'll find via a fairly simple argument that it must be the case then that the velocity is equal to 0, the pressure is 0, and the fluid is completely flat, so that the free surface function is equal to 0. And what that tells us is that if we want to produce a non-trivial traveling wave solution, we have to have an external source of stress or force. In particular, we need something like T here in order to overcome the dissipative effects of viscosity. Now, if you think about this physically, this is not surprising at all. And viscosity dissipates energy from the fluid. And so in order to have a traveling wave solution, you have to have something that is going to provide energy to the system to balance the dissipative effects of the viscosity. And it is in fact exactly this external stress that will provide the power to the fluid that is compensated by the dissipative loss. Okay, so on the other hand, let me give you a history of this problem. Most of it has to do with the inviscid case, where we set viscosity to 0 and basically remove the Laplacian in the story that I was telling you before. In that case, the story is very, very old, and I could not possibly attempt to survey all of it here. There's more than 150 years worth of work on this topic. Effectively, the point is that without viscosity, it is possible to produce solutions without sources of external force. This was done initially for 2D irrotational fluids over the course of about 100 years, culminating in the construction of what are called Stokes wave solutions. Much more recently, in the last 20 years, in fact, progress has been made on the rotational problem, where the fluid is not posited to be curl-free for all time. This essentially started with the work of Constantin and Strauss and propagated from there by the various students of Constantin and Strauss for the most part. And by now, it's also known that a little bit of we have a little bit of knowledge about what happens in 2 dimensions when there is a model of surface forcing or wind. In particular, the work of Wheeler and Sam Walsh has established some of this. There is a little bit of theory that is known in 3 dimensions, but not a ton. What is known in 3D is all irrotational by several groups of authors. Let me mention what is known or what was known in the viscous case. Essentially, all that was known in the viscous case is what corresponds to the fully stationary problem when the wave is not traveling, so where gamma is equal to 0. And in this situation, strangely enough, there are not actually any results that I'm aware of for the sort of slab geometries that we're talking about. They're more for more specialized geometries that model things like reservoirs and things like that. When gamma is not 0, the only results that I'm aware of are some very nice experimental results by various groups. And actually, this is how I came to start working on this problem. Was I saw some of the experimental results by Masnadi. And what these results do basically is do what I was talking about in terms of the tube blowing air on a fluid. They put up a wave tank in a lab, and they mount above the wave tank a tube that blows air on the fluid at some particular rate. And this whole mechanism is then mounted on a system that allows it on a track that allows it to move at a constant speed. And they mount a camera in the same frame as the moving tube. And what they find is that in certain parameter regimes, they can actually move the thing along in a way where it looks like there's actually a traveling wave solution to the fluid moving along. And of course, they can put different types of fluid into the wave tank, and they're in particular able to put ones where viscosity is not negligible. So this is all strong experimental evidence that these types of waves do actually exist. And so one of the goals initially was to show analytically that we can actually construct things like this. So here is a very rough statement of the theorem. I have sort of suppressed a lot of the details, and this is only a special case. So this only corresponds to a particular type of stress. The actual theorem we prove is more general. So what we show is that if you're in dimension 2 and you have either no surface tension, which means you set sigma to 0, or you have surface tension, which means you set sigma positive, or you're in dimension 3 and you have surface tension. So if you're in 3 dimensions, we require surface tension in order for a theorem to work. Then there exists, well, then what you can do is you can take a supercritical regularity parameter S, and we can build then an open set WS contained in this product. So what is this product? This is where the wave speeds are going to live. And this is a standard Sobolev space, HS plus a half, which is the space in which our external stress is going to live. So this is basically saying this space WS is where our traveling wave speed and the external stress are going to live. And we can also construct a Sobolev type Banach space XS such that the following hold. So the first observation, or the first point, is that our curve of trivial solutions, which correspond to any value of gamma, let's say not equal to 0 in this case, and 0 forcing, this will sit inside this open set. So in particular, our open set is quite big and contains all non-zero values of gamma, along with the trivial forcing 0. So in other words, if you fix any value of gamma, you will get an open ball in HS plus a half, for which we will be able to produce solutions. The other thing that we have is that the space XS enjoys a supercritical embedding. And what that means is, so the space XS will contain triples of functions, V, Q, and eta, which will be our solutions. And if V, Q, and eta live inside this space, then there's a certain type of Sobolev type supercritical embedding, which will tell us that V is continuously differentiable up to at least order 2 and has derivatives up to order 2 that are bounded. The velocity field will be classically differentiable up to order 1 with bounded derivatives. And the free surface function will be classically differentiable up to order 3 with derivatives that are not only bounded, but that decay to 0 out at infinity. So this is the sort of functional setting of our theorem. The result actually says, this is the main result here. And what it says is that for every pair gamma t belonging to this open set WS, there exists a traveling wave solution VQ eta in this container space XS that solves the traveling wave equations classically. So these are not weak solutions or strong solutions, they're point-wise classical solutions. The solutions that we construct are locally unique, and they satisfy various estimates. For instance, that we have nice control on the magnitude of eta, so that the set omega b plus eta is nice and satisfies the various conditions we want. Moreover, the map that takes a pair gamma t and maps it to the solution pair VQ eta is going to be locally Lipschitz. So in other words, we have continuous dependence of our solutions, not only on the wave speed gamma, but also on the forcing T, or sorry, stress T. So here are some remarks about our result. So our free surface function goes to 0 out at infinity. And in the traveling wave Euler world, these are what are called solitary waves then, because it means that our perturbation sort of exists locally, and then out at infinity, it sort of goes to 0 and becomes quiescent. The second thing I want to mention is that this space XS, which I have not told you, the reason that I have not told you is because it involves new Sobolev type spaces with very strange properties. So these are not standard spaces. These are the spaces that were cooked up specifically for this problem and have very odd features. The other thing I want to mention, which is rather curious, is our technique is capable of producing solutions for every gamma not equal to 0. So for any traveling wave velocity that is not zero, we can produce solutions. However, our technique does not work in the case when gamma is equal to zero. So there's something a little bit strange about this and a little bit counterintuitive, but essentially what I'm going to attempt to tell you is that the traveling wave speed actually plays an essential role in defining the topology of this space XS. And if you were to set gamma to be zero, then the topology would change in a way that will prohibit us from producing solutions. And so really the fact that the waves are traveling is an essential feature about their construction. Let me also mention, so the result I told you on the previous page is just a special case of what we prove, meant to make the exposition simpler in this talk. In the actual paper, we prove a more general result that has a more general version of the stress and also has bulk forces, but it's more difficult to write down in that case. The other thing I want to point out is our result actually holds in arbitrary dimension bigger than or equal to 2. So if you care about 4-dimensional fluids, our result is applicable. And finally, I want to make the remark that in recent work with my student Noah Stevenson, we have extended the theorem to handle the case of multiple layers of fluid with different viscosities and different densities as well. Okay, so for the rest of the talk, I basically want to give you a sense of how we prove this result. The first thing that we need to talk about is how we can rephrase the problem in a way that we can bring to bear the standard PDE tools. And if you know something about free boundary problems, you know that the very first thing that you do when you're studying a free boundary problem is rephrase the problem via a coordinate transformation in a domain that's not moving in time so that you can use standard techniques. And we do that as well. We just do not use the standard tool of Lagrangian coordinates, which is something that you often use in this industry. What we do instead is we are going to rephrase the entire problem on the domain omega, which is the equilibrium domain. So it's just a cross section crossed with the vertical interval 0 to b. And the way that we're going to do this change of variables is in the absolute simplest possible way. We're just going to take each of the vertical fibers that lie above a point on the cross section, and we're going to do a linear distortion of that fiber from the set 0b into the set 0b plus eta. So we just make a linear change of variables in each of the vertical directions. We do nothing at all in the horizontal direction, and this will be what we will call our flattening map F. And you see that one of the things that this does by construction is it does absolutely nothing on the bottom. It stays the identity there, and it maps the top of omega to the moving surface, or rather to the unknown free boundary sigma b plus eta. The other crucial point is that this set F is going to inherit the regularity of eta in an obvious way, because you can just look at this and see that the regularity of eta is going to dictate the regularity of F, because everything else appearing in this thing is going to be nice and smooth. So using this change of unknowns, we can rephrase the entire problem on the equilibrium domain omega by introducing new vector fields U and a scalar pressure P just by composition with our flattening map. So V was our previous unknown, U is our new unknown that will be phrased in the equilibrium domain. When we do this, we arrive at an equivalent system of equations that we call the flattened traveling wave system. This looks a lot like the system that I wrote before. The only difference is that all of the differential operators that I write have the subscript A on them. What does that mean? Well, when I make a change of variables, every time I take a derivative in the domain omega, in the moving domain, in the flattened domain, that's going to correspond to the linear combination aij dj summed over j there, where a is the inverse transpose of the derivative of my coordinate change, of my flattening map. And so making this change, every time I have a gradient, I replace it with an A gradient. Every time I have a divergence, I replace it with an A divergence, Laplacian, et cetera, et cetera. So all of these differential operators are defined in a natural way by just replacing their standard counterparts DI with these more complicated objects, these A derivatives, if you want. The point is that the derivative of f will involve the derivatives of eta, the free surface function. And so when you look at this system of equations now, it becomes completely clear that this is a quasi-linear system of elliptic equations. And so effectively, this is a general feature of free boundary problems. Even if you have what appears to be a linear equation in an unknown domain, when you pull it back into a fixed known domain so that you can use the standard PDE classifications and the standard tools, what you find is that you actually have a quasi-linear problem. So the free boundary part is always going to induce quasi-linearity in your PDEs, which of course is going to make this a fairly nasty set of equations to study. So as should be sort of obvious from the form of the results that I've given you here, this theorem is going to follow from an application of the implicit function theorem. I mean, if you look at the way this is phrased, it very much looks like a byproduct of the implicit function theorem. And indeed, that is what we're going to do. So we're going to attack this problem using the implicit function theorem to solve for our unknown triple up and eta in terms of gamma and t, which are given. And of course, we're going to do this around our trivial solutions, which correspond to t is equal to 0, up and eta equal to 0. And if we do this, when we linearize around the trivial solutions, we get a linear version of the problem from the previous slide that I'll call the Gamma-Stokes system with traveling gravity capillary boundary conditions. So this system BGC sub gamma. And in this, what we find is something that looks like a version of the Stokes system in the top equation, a sort of mixed then set of boundary conditions involving the stress and the normal trace of the velocity field, and then the no slip condition on the bottom. So this is some sort of linear system of elliptic equations. And the way that I've written this is with boundary forcing f, g, h, and k, because of course, if I'm going to apply the implicit function theorem, I need to know that I have an isomorphism. So I'm going to need to study this problem with generic data on the right-hand side. So if you're like me and you stare at this problem for a couple minutes, you think, well, something very nice is going to happen if I take gamma to be equal to 0 in the system. Now, something nice happens both mathematically and also that is reasonable from a physical perspective, because initially when Giovanni and I started working on this problem, we thought that if we took gamma to be 0, we would then be able to produce solutions for gamma very, very small. Which seemed like a reasonable hypothesis when we were constructing, when one tries to construct traveling wave solutions. The idea is that if you move the forcing term very, very slowly, maybe you're more likely to be able to actually construct solutions. Turns out that if you do this, though, something unfortunate happens. But let me tell you the mathematical nicety that happens if you set gamma to be 0. What happens in this setting is this problem that I've written here, which involves unknowns up and eta, decouples into two distinct systems of equations. In the first system, you can solve for u and p just in terms of f, g, h, and then the horizontal component of k. And then once you have solved for u and p, you can take those things together with the vertical component of the vector field k and feed them into an elliptic equation for eta, which is a beautiful equation. We can obviously invert this thing in principle, and then you would solve for eta. So this is a very clear strategy for attacking the problem when gamma is equal to 0. But unfortunately, it runs into a fatal problem. And that problem is this. If I look at my first system of equations here, which is how I will determine u and p, what I'll find is that if we do elliptic estimates on this problem, say in the scaling where f belongs to the space hs, then what I'll be able to show is that the velocity field belongs to hs plus 2, but I will not be able to show that the pressure belongs to hs plus 1 in the way that you would expect. Instead, because there is no appearance of p itself in this system of equations above here, the best that I will be able to get as an estimate from this system is that the gradient of p belongs to hs. Now, this may look harmless, and if I were in a bounded domain, this would be harmless because I could always just subtract off the average of P in order to get an estimate for P in terms of the gradient using some sort of Poincare estimate. But remember, our domain is an infinite slab, so I have no such Poincare inequality, and I can't subtract off a constant. And what this means then is that the best excuse me, the best estimate that I can get from this first part of the equation is that the gradient of P belongs to HS. Now, the reason this presents a problem is I'm supposed to then take a trace of the pressure and use that as data in this elliptic problem on the boundary. And so the question then becomes, well, what is the trace of such a function P? Is it in a standard Sobolev space? And will I be able to use this, this equation to actually solve for eta? Unfortunately, what we find, what Giovanni and I found when we looked into this is that if I look at the estimates available for this problem, where the gradient of P, or where P belongs actually to the homogeneous Sobolev space H dot 1, then in fact the trace space associated to this thing was not known. It was something that we had to work out, and it is a non-standard fractional homogeneous Sobolev space. And it has some degree of regularity to it, but the regularity that you get and the estimates that you get are not sufficient for inverting this problem. And what I mean by that is if you take the estimates that you get and you plug them in and you use them to solve for eta, the resulting eta that you get, you can't show that it's bounded. And what's worse than that is we can't even show that it's a function. So in some sense, the best that you can get is that it's an equivalence class of tempered distributions. You know, we're trying to use eta as the actual graph that we use to generate an open set. So an equivalence class of distributions is not going to be good enough for something like that. So this technique just fails spectacularly. And so we were forced then, after studying this problem, to sort of give up and try again. And so what we're going to do is we're going to say, all right, well, maybe this idea of setting gamma to be 0 was faulty. Maybe we need to look at the case where gamma is non-zero, in which case this decoupling that I described before is not possible. And so to get a sense of what happens to the resulting problem, you see, this is a fairly complicated system where we have 3 unknowns, P, U, and eta. So the first thing that we can do if we want to make our lives simpler to try to understand what is happening in the system is to imagine that somehow either we're given eta or we just sort of ignore it. And if we do that, excuse me, then what happens is we end up with an equation just for U and P, but it is an overdetermined problem in the sense that we specify too many boundary conditions. So that there are too many conditions for the number of unknowns that we have in the system. And the reason for that is entirely due to the system of boundary conditions that I've underlined here. So the idea is that if you break this down to a scalar count of boundary conditions, this is n plus 1 boundary conditions. There are n that are coming from this system here, and then there's plus 1 coming from here. So there's n, and then there's plus 1. And the thing is, if you look down here, for instance, I can specify n at the lower boundary. And so in general, we only expect to be able to specify n conditions. So specifying n plus 1 appears to be problematic. And in fact, we can make this rigorous in the sense that if I ignore this condition here, where I specify the normal trace, the resulting system of equations, which we call the gamma-Stokes system with stress boundary conditions, because you're just specifying the stress, this problem is well posed. So this is something we prove in the paper. And the idea here is that for every gamma, you can choose an appropriate scaling of Sobolev spaces where this is where my velocity field will live, and this is where my pressure will live. And this will map into a space of data, F, G, and K, just as I wrote them down in the previous problem. So this is my F, this is my G, and this is my K. And the map that you get by looking at this PDE, where we ignore this condition here, induces an isomorphism. And in particular, given any F, G, and K in this regularity class on the right, I can solve this problem uniquely for a U and P in this regularity class on the left. And so what this means then is the problem is already well posed without specifying this final boundary condition. And so we do not have the freedom to just specify another boundary condition. If we want to specify another boundary condition, though, we can try, but we're going to be forced to deal with compatibility conditions. To get a sense of how these work, let's start off with the simplest one of these. These, of course, everyone who works in PDEs is familiar with these from, let's say, studying the Neumann problem for the Laplacian. But let's review how this works. So in particular, part of the problem that we're trying to solve for the overdetermined problem requires that the divergence of U is equal to G. The normal component of the velocity field is H on the top and 0 on the bottom. So if everything were nice and integrable, what I could then do is do the same thing that we do for the Neumann problem. I just integrate G, which is the divergence of U, over my set omega. Apply the divergence theorem, and what I'll get is then the integral of the normal component of my velocity field on the top, which is just H. And this will then tell me a compatibility condition between the integral of G in the bulk and the integral of H on the top. However, there's a problem using this in our formulation because we're working with L2-based Sobolev spaces in a domain that has infinite measure. And so we're never going to be able to verify that things actually belong to L1. So this simple calculation is not going to be available to us. Instead, we have to come up with a sort of distributional version of this where we hit this system of equations up here with test functions and move things around. And eventually what we can find is that the function H, which is a function on the cross section, minus the function that we get from G by integrating from 0 to B in the vertical direction at every point. So this is just a function on the cross section. This has to belong to the homogeneous Sobolev space H dot minus 1 on the cross section. Now, this looks completely bizarre and seems to have nothing to do with what we derived above. However, if I take this identity that I derived above and I rearrange it and apply the Tonelli-Fubini theorem, what I find is that it tells me that the integral of this quantity in parentheses, H minus the integral of G, has to integrate out to 0, has to sort of have average 0. If I think about that on the Fourier side, this is equivalent to the quantity in parentheses having vanishing Fourier transform at the origin. Now, the condition that this quantity here belongs to H dot minus 1 does not require, strictly speaking, that the Fourier transform vanishes at the origin, but it's a sort of weak formulation of that in the sense that it requires that there are this function is not too large at 0 because it has to be integrable when we multiply it by this negative weight and integrate near the origin. So this is still something similar to what you get in the L1 formulation. It's just a little bit more complicated because we're working in an L2 framework. Okay, but so this is not the end of the story. This is not the only compatibility condition. It turns out that to figure out the second compatibility condition, we have to take a cue from the closed range theorem and work with the adjoint to our overdetermined problem. And interestingly enough, the overdetermined problem's adjoint is an underdetermined problem, which I have written here. And so this is basically the same Stokes system with the same boundary conditions on the bottom, except the difference is that on the free surface, or on the unknown, or on the top rather, instead of specifying in boundary conditions, we specify n minus 1. We only specify the first, like the horizontal part of the applied stress. Now, this just comes from a calculation. You compute the formal adjoint. What's nice about the underdetermined problem is if you think about the isomorphism I described before, it would apply to this problem if we augmented the underdetermined problem with an extra boundary condition. And so we can do that. We can explicitly characterize the kernel to this underdetermined problem by adding in a final boundary condition that the normal component of this boundary condition here is some specified function phi in an appropriate regularity class, and then hitting the problem with the isomorphism that we talked about earlier. So all solutions to this problem can be characterized by our isomorphism applied to the triple 0, 0, phi E in. So we completely understand or can parameterize the kernel to the underdetermined problem. And what this means is that I can mimic the argument that we use in the closed range theorem in order to derive another compatibility condition. And the way that that works is we basically say, look, if there exists a solution UP to the overdetermined problem with a data quadruple F, G, H, and K, then what I can do is I can multiply by a solution to the underdetermined problem, integrate by parts, and deal with all of the boundary conditions in an appropriate way. And if I do this in the right way, what I will ultimately find is that the data F, G, H, and K have to satisfy this integral identity. That tells me that the integral of F against V minus the integral of G against Q, where V and Q are determined as above here via this isomorphism, minus the integral of K against V on the top, minus the integral of H against this arbitrary function phi, this has to vanish for every appropriate choice of phi, meaning in an appropriate Sobolev class. And so what we end up with is a sort of, I don't know, you can kind of think about it as a sort of orthogonality condition in some sense. This integral condition tells us that the data cannot be specified arbitrarily, but they have to satisfy this integral identity in order for there to be a solution. This is a necessary condition for the existence of a solution to the overdetermined problem. It turns out that these two compatibility conditions are both necessary and sufficient. This is a quite convenient thing, because what it allows us to do then is to say that the overdetermined problem is actually well posed, provided that I restrict it to the set of data that satisfy the two compatibility conditions. And so our theorem says that if you give me a data quadruple that satisfy the appropriate regularity hypotheses and the compatibility conditions, then we have unique solvability of the overdetermined problem. And we can rephrase the unique solvability as an isomorphism between a standard Sobolev class for the velocity field and pressure, and some strange class of functions that I'm not going to specifically tell you that we call Z for the data tuple. And the data tuple here, the norm encodes these regularity properties as well as the compatibility conditions in some way. Okay, so the point is we now completely understand the overdetermined problem. So the question then is, what can we do with this? Can we actually use this to solve the original problem that we were trying to solve in order to use the implicit function theorem? The answer is yes, but to get to that, we have to reformulate the second compatibility condition. And the reason for that is because it's inconvenient to work with in this sort of integral form, where we have this sort of orthogonality condition for all phi. So it turns out you can reformulate this on the Fourier side just by applying the Fourier transform. And if you do this, you get rid of the sort of the test function phi, if you want, and you replace it with an almost everywhere condition in terms of the horizontal Fourier frequency, which I've written here. Let me mention that these functions v and q, these are special solutions to ODEs in the vertical variable only that, roughly speaking, correspond to the Fourier transform of something like a Green's function to the applied stress Stokes problem that I mentioned before. So these are things that in principle we can explicitly compute on the Fourier side as solutions to some ODE. This pointwise condition is much more convenient to work with. And the reason for that is what we can now do is return to our original problem, the TGC gamma problem, where we have returned the function eta. And what we know is we can say, well, look, if I have a solution to this problem, then I can view eta as part of the data. So I can move this term onto the right, and I can move this term onto the right, and then I have then necessary and sufficient conditions in terms of the data plus eta in order to solve the resulting problem. So our compatibility conditions must then be satisfied by F, G, H minus gamma times the first derivative of eta, and K plus this gravity capillary operator hitting the free surface function eta. Now, so there are two compatibility conditions we have to worry about. The first one of them is not really an issue, and I'm going to ignore for the purposes of this talk. The more interesting one is the second compatibility condition. So what happens is if I take my second compatibility condition, which I have now reformulated on the Fourier side, and I plug in these conditions, these bits of data with eta involved, what I get is an equation for eta that allows me to solve for eta on the Fourier side in terms of the data on the Fourier side. And in particular, what I end up with is a pseudo-differential operator with symbol rho where the data is a function, at least on the Fourier side, psi, that is computed in this explicit way in terms of the forcing f, g, h, and k, and these functions that we previously talked about, capital V and capital Q. Now, the symbol for my pseudo-differential operator is unfortunately not explicit. It's fairly complicated in the sense that it has this term coming from the traveling wave operator. It has a term coming from the gravity capillary operator, but then it has this v-in function, which we saw before. And the thing is, we don't have a clean, explicit formula for it like we have for these other things. So if I'm going to be able to solve this problem and get good estimates for eta, I'm forced to understand this symbol v-in. Now, let me give you a little bit of a sense about what this thing is. This function v-in, it turns out, is the symbol associated to the following pseudo-differential operator. And what it does is it's going to take a function phi, which is defined on the upper free surface, and it's going to map it to the normal component of a velocity field traced onto the top again. So it will then be a mapping from hs into hs plus 1 on the upper surface. And the velocity field that we construct as an intermediate is a solution to the Stokes problem with forcing phi on the top. So what this boils down to is this is what we call a normal stress to normal Dirichlet map, in the sense that we take a function phi, we use it as normal stress data in the Stokes problem. We use it to solve for a velocity field and pressure, and then we take the normal trace of that velocity field onto the upper free surface. So this is like the analog of the Neumann to Dirichlet map that you study when you study the Laplace operator, but done for the Stokes system in place of the Laplacian. And so what we learn from then looking at the symbol of our operator rho is that in a very interesting way, rho synthesizes all of the different boundary conditions that appear involving the free surface function. So it synthesizes the traveling wave operator, gamma d1. That's what gives us the first part of the symbol. It then has a part that corresponds to the gravity capillary operator, which gives us this part of the symbol. And there was a final part of the symbol which is not explicit, but it's coming from this normal stress to normal Dirichlet operator, which is this function v sub n. So the point then is that if I really want to, if I'm going to use this system of, or this equation here to construct eta, I need to understand rho. And if I want to understand rho, I have to understand v sub n. So we can do this, and Giovanni and I then undertook a very long and painful set of calculations to explicitly compute the asymptotic expansions, at the very least, of this symbol v sub n. After we did this, what we were able to find is that the symbol does vanish. So rho is 0 at the origin. Fortunately, that is the only place where it vanishes. So I can divide both sides of this equation by rho in principle to define eta hat, at least for frequencies away from 0. And then what we find is that we can explicitly compute the asymptotics of rho. When we have positive surface tension and the dimension is 3 or higher, what we find is that for high frequencies, we have a standard Sobolev multiplier that looks like it corresponds to a derivative. For low frequencies, though, we have this sort of weird mixed behavior where we have one part that looks like C1 squared and another part that looks like 2 derivatives. On the other hand, when we're in dimension 2, and we allow the surface tension possibly to vanish, what we find is that since if the ambient dimension is 2, the dimension on the boundary is 1, and that means that C1 is equal to Xi. So we get full control of Xi squared in this case. And then at high frequency, it turns out you can also use this operator gamma d1 to get elliptic control for high frequencies as well. And the key point is that in one dimension, the differential operator just d1 is an elliptic operator, and so you can use it to gain regularity at all frequencies. So the biggest difference between these two things is that at when the dimension is 3 and higher, there's this term involving gamma squared C1 squared at low frequencies. So something very strange is happening where we get a weird multiplier at low frequencies. So if we take these estimates for the symbol and we plug them in, what the best estimate that we're able to get is in terms of the thing that we control on the right side here. This is synthesizing all of the information that we have in terms of the data, both in terms of the regularity and the compatibility conditions. So this is essentially tight. This is the best we can control on the right. And this is then the best that we can control on the left when we use this equation to solve for eta. And so the point is that for high frequencies, what we're getting is standard HS plus 5/2 estimates for eta. This is completely standard Sobolev control. When the dimension is 2, at low frequencies, we also get standard Sobolev control. So we're getting basically a standard HS plus 5/2 estimate when the dimension is 2. However, when the dimension is 3, which is in some sense the dimension we actually care about, our low frequency multiplier is something very strange. It's this function right here. And you can see this does not provide standard control in a standard Sobolev space. So this is not something we can use to get standard Sobolev control, and therefore we're forced to work with this in a new framework. Okay, so in dimension 3 and higher, we're forced to come up with a new function space to work with. Let me also point out here that this is where gamma not vanishing becomes essential, because it turns out this term right here is going to be very important, because otherwise we just get c squared here, and that's not good enough to construct eta as a function rather than as a tempered distribution. So we're sort of forced to work with what the problem gives us. And so what we do is we define a new type of anisotropic Sobolev space we call XS. And it just takes the symbol that we get from the problem and uses it on the, as the definition of a norm. Now, fortunately, what happens is we get a Hilbert space out of this. This is a nice function space. It contains the standard Sobolev class HS. So it's something that's strictly bigger than the usual Sobolev spaces. And then a technical miracle occurs where the inverse of this low frequency multiplier is integrable. And what that means then is for the low frequency part of my function f in this function space, I can guarantee that it's in L1. And so the low frequency part will be both band limited and in the Wiener algebra. So it's going to have all sorts of very nice properties. And so what that means is we can decompose the functions in this space into the low frequency parts, which will be smooth and decay very rapidly. Or well, not necessarily rapidly, but will go to 0. Plus something that's in a standard Sobolev space at high frequency. So we have a nice functional framework in which to work. Unfortunately, weirdly enough, this space has very strange properties. So for instance, it's not closed under composition with rotation. So you can find a function that lives in this space such that if you compose it with for instance, in 2 dimensions, if you compose it with a 90-degree rotation, you leave the space. And the reason for that is because of this anisotropy that we see in the Fourier symbol that defines the norm. Nevertheless, we can use this space to attack our problem, and we find that it has good embedding properties and good nonlinear functional analytic properties, which are good enough for closing the problem, closing the analysis. So I'm running a little low on time here, so I think I'm going to skip this slide, but let me just sort of quickly summarize and say we also need a custom Sobolev space for the pressure. But what we can do is once we have identified these custom Sobolev spaces, we then have the capacity to prove that our full traveling wave problem for UP and eta actually is uniquely solvable and induces an isomorphism. Once we have that, then the question then becomes, can we actually use the implicit function theorem? And for that, we can. So the idea basically is we're going to go back and take our flattened traveling wave problem, view it as an implicit function theorem argument of the form some nonlinear mapping is equal to 0. And then what we notice is that when we compute the appropriate linearization of this thing, we arrive at the operator corresponding to this traveling gravity capillary equation that I mentioned before. And this means that we can then use the implicit function theorem to produce our solution. And let me just mention finally, very briefly here, all of this solves the problem in the flattened coordinate system, but we can then undo this transformation and go back to the original coordinate system as well. So after flattening and attacking the problem in the flattened coordinate system, we can actually go back and solve the problem back in the, let's say, Eulerian frame. So that's a rough idea of how we do this. Let me say thank you for your attention, and I'm sorry to run slightly over here.